Hello, good evening, good afternoon to everyone. We are about starting today's session.
Okay, you should be able to see my screen at this stage. I have a PowerPoint presentation open that I will use to draw some things. All right, so welcome to this first lecture of the Quantum in Pictures series. My name is Stefano Gogioso. I am a lecturer at the University of Oxford, and I also do work for a small startup that develops quantum software. So quantum has been my primary field of research for many years. I studied at the University of Oxford prior to working for them, and I learned quantum using the very same diagrammatic sort of pictorial approach that I'm going to introduce today and that my colleagues from Quantinuum will introduce over the coming lectures in this series. The main idea is that instead of talking about linear algebra or vectors, matrices, operators, some of you may be familiar with some of these terms, hopefully. Some of you may not, in which case, bear with me. You'll probably get the most out of the diagrammatic perspective, but I will also try to draw some connections to the more traditional presentation of quantum theory and quantum information, quantum computing. So I will draw some equations, I will draw some vectors and matrices just to give an idea of what's going on. If this is something that you're not with which you're not familiar, then this is you can disregard it and just listen to the more high-level conceptual things. And the main idea is that instead of starting our discussion from some linear algebra and some vectors, matrix numbers, quantum states, we take a broader approach and we think about, I'm going to put it to the maximum that my microphone allows. Maybe I can try and, yeah. Would this be better? Maybe this is slightly louder. We don't really think about particles from the very start. We think about some abstractions of particles and the ways that particles move and transform, which we call wires and boxes. Some analogies might be helpful to get started. Imagine that you have a battery, and this battery is connected to a switch, and this switch is connected to a light bulb. And so you can think that there is a current that flows. Now, the specifics, obviously, current has polarity, it flows up, back, and forth. If you think of electrons, electrons will flow both ways. But if you just imagine conceptually that there's some current that flows from the battery, the source of the current, at least the source of the energy, I guess, through the switch, which does something, maybe it lets it pass through, maybe it doesn't let the electrons pass through, all the way to the light bulb, where this ends and then something else happens afterwards. And so you sort of conceptualize, you split this into various building blocks, where you have some parts of the process, which are your boxes, which are where stuff happens. So there's three boxes here. Let me pick a slightly different color that might be easier to see. There's three boxes, 1, 2, and 3. These are boxes, 1, 2, 3, which is where stuff happens. Okay? And then you have a wire that carries your particles or carries your, in this case, electricity from one box to the next. So you can imagine that you start from this box, you end up into this box, then you start from this box, and you end up into that box. Or a different example could be that you have a pump, and the pump is kind of a source of water. And so this is a box. And there's a hose which carries the water from the pump to, let's say, the flowers in your garden. This is a wire in our nomenclature. And you then have a place where something happens to the water again, like the flowers absorb it and then they grow, hopefully, and become beautiful. and that is a different box. So you can really, we have two things that we have to think about. There's just conceptualizing where particles are, where electricity is, where water is, where it enters and exits. Those are boxes. The things that carry it are wires for us. So the hose is a wire, the electrical wire is a wire, and so on. And we kind of straighten things out a little because it's good to have, of course, it's good to have like pictorial representations, but it's also good to have some standardized like graphical notations to make things simpler and easier to draw and reason with. And so instead of actually drawing a battery or a switch or a light bulb, what we typically do is draw some boxes, literally as boxes, as like rectangles, maybe with some wonky shapes. Sometimes it helps. But we have wires that carry from one box to another box, and you have boxes here that do something to the electricity. And as a convention, we draw our boxes with time flowing upwards. But you could draw them going left to right. That is, for example, the convention in quantum circuits. So it really depends on your applications. If you're reading a quantum circuit, then you tend to read things left to right, like the initial state is at the left, things get changed, and the final state is at the right. If you, like in this course, in these lectures, the convention we'll use is that we draw the initial stuff at the bottom, then as time progresses, we go upwards, and the final stuff at the top. And this is closer to what happens in some general relativity diagrams. So if you've ever done some physics diagrams, you typically draw like light cones, and you have the future light cone and the past light cone, and time goes up, and you have some event. These are not very different. In that sense, the convention is that time is vertical and space is horizontal, but you could have other conventions. And quantum circuits, for example, are rotated the other way around. The other example I gave was the pump, where we have flowers and water that gets carried. Instead, in the case of the light bulb, it was electrons or electricity, I guess, that get carried. And again, this is the kind of metaphor that we use, that there's boxes where particles or water, electricity goes in, comes out, and wires which connect them. But really, we are interested in quantum theory, and so our wires don't carry electricity. Our wires carry quantum particles of some kind, typically of only one kind, but in general, you can have multiple kinds of particles that are carried by wires. And so you can really imagine that in our diagrams, what goes around this wire, for example, are photons or electrons. Okay, so that would be a kind of particle. And if you've seen some diagrams from physics, sometimes people draw these diagrams where there's particles that interact between themselves to draw some physical process, like two electrons that interact with the electromagnetic field and get either attracted or repelled. And those are very similar to these diagrams, where you have something like two electrons coming in, and then there's some interaction between them, and then two electrons coming out. This is an example of a kind of a shape of a diagram that you could see in physics. And sometimes you know something more about this interaction. You know that it actually is mediated by some photon, which is exchanged between them and causes their deflection. And so you can refine that diagram by saying, oh no, it's not just the electrons themselves. Actually, there's some boxes and there's some photon in between that, let's say, one electron emits a photon, the other electron absorbs a photon, and we get something like this instead. So two electrons come in, a photon is exchanged, and two electrons go out. And this is kind of an interesting example because I have shown like now multiple boxes that are connected with a wire in between, and I have had to make sure that when I plug them, I can plug them almost any way I want, as long as I respect the type, the stuff that's carried on the wire. So one thing I can't do is take a wire that carries water. There's a pump, this carries water. And then there's a wire that takes electricity. and I cannot connect those two together. But everything else I can connect if I want. So the only rule that I have, I can draw my boxes and I can wire them however I want, but the only rule that I have to respect is that the types, the kind of stuff that's carried by the wires that it wins when I connect them is the same. Otherwise, I get an invalid diagram. I get something which doesn't work. I try to connect a garden hose to an electrical wire, that sort of stuff. And that's not good. Luckily, in this particular, in this lecture series, all wires carry qubits. So no issue, there is no problem. But it's something that you do encounter if you do something like you try to connect a process that emits an electron, and you try connect it to a process that expects a photon. So you have an electron comes out here, and the next process takes a photon. And if you try to do this in your lab, you're going to be very, very disappointed. It's not going to work. Like whatever you try to do is not going to give you a good experiment. It's not going to work out. So this is a problem. You don't want to do this. This is a no. Can't connect it that way. But here we'll talk about quantum particles of a single kind, so we never have that issue, and we don't really have to annotate our wires by saying it carries photons, it carries electrons. No, they only carry some kind of a simple particle called a qubit, and so that's the extent of our checks. Our checks are done. We can connect our boxes. Our wires can be connected however we want for the remainder of this course. But there are more complicated scenarios where that's something to keep in mind. So a bit more abstractly, in terms of sort of quantum theory, more traditional presentation, what is a wire and what is a box? So a wire just represents a qubit, really. It's just a way of saying a qubit, or if you want to be a bit more precise, it's a pair of complex numbers. That's what it carries. Okay? So here, along a wire, what goes is just a pair of two complex numbers. A normalized complex vector. That's what gets carried by the wire. So a wire is simply a way to say something goes from one place to another. It doesn't really have any particular significance other than that. A box, on the other hand, is more interesting because a box is something that takes one qubit and one or more qubits, because it could have multiple wires coming in, and returns one or more qubits, because it could have multiple wires going out. In this case, it's something that goes from a single qubit to a single qubit, because there's only one wire in and one wire out. And so it's a matrix. It's a linear map. So let's say it could be a unitary, but more generally, it could be some other map. So I'm going to call it U, I guess, for consistency with other things you might have read. But really, all it is just a matrix. So these are more generally, you could have wires with multiple wires. Sorry, boxes with multiple wires coming in and going out. And I will tell you in a second what those correspond to in more traditional terms. But before I go there's some special cases, which are known as states and tests, which correspond to recipes to create a qubit or one or more qubits out of nothing, and something that takes a qubit and consumes it, one or more qubits. So a state is a recipe to create a qubit. And a test is a recipe to consume a qubit. Okay? So these recipes correspond to just the typical states and effects. So in traditional terms, this would be a ket. and this would be a bra. But we don't draw them as cats and bras because it becomes very hard once you have more than one qubit to make this work nicely. If you're familiar with Dirac notation, for a single state, this is good. If you've done some quantum mechanics for a single state, Dirac notation is good. Once you have multiple states connected in weird ways, we'll see that it becomes a bit more complicated. And so the diagrammatic notation helps you box in some of this complexity and makes it easier to manipulate and understand what's going on. All you have to think is, okay, I have boxes, some qubit states come out, some qubit states go in, something happens in between, which depends on what the box is. And that's it. That's all you have to know. You sort of keep the complexity in until you really need to take it out to do computations. And what my colleagues will say over the coming lectures is that you don't, most of the time, in fact, almost all of the time, you don't have to look into the boxes. There are equations that you can apply between the diagrams themselves that allow you to simplify the diagram and do the calculation without ever having to look at the complex numbers that live inside, or at the more traditional way of representing the contents of the boxes. Now, having a single box or a single wire, this would be, I guess, in general, a linear map. Not necessarily a unitary, which is important. That's a difference between the quantum circuits formalism and this more general diagrammatic formalism, is that we can talk about things which are not unitary. But that's for later. First things first, what do you do when you have multiple boxes? The one box, yeah, great. It's not particularly useful. Maybe it's interesting, but it is not quite as interesting as having multiple boxes, wiring them together to get a more complicated system. Okay, you have a battery. What do you do with a battery? You wire it into a bulb. What do you do if you want to turn off the bulb? You wire the battery into the switch and then the switch into the bulb. And so you need ways of composing these boxes. You have some simple boxes, you compose them together to get something more complicated, a circuit or a diagram. And there are two basic operations, two basic ways of composing boxes. One of them is sort of sequential composition. Again, time goes forward and space goes sideways. So sequential composition is one box after the other. Take the output of a box and plug it into the input of another box. So if you think that these are linear maps, right? You have F, and then you have G, let's say. F takes a qubit into a qubit. G takes that qubit, returns a qubit again, something like that. And the sequential composition is just the composition of the two linear maps. Again, goes from a qubit to a qubit. Nothing special. Now, if instead you have two boxes and you put them side by side, they are happening in time, but independently, sort of in parallel, independently of each other. So they're not simultaneous. It doesn't really matter if one of them is higher or lower, because the effect doesn't depend on time. There's no specific time parameter here. It's just sequential composition or parallel composition. And the idea is that if you have two of these boxes and each of them corresponds to a linear map, again, let's say F from a qubit to a qubit, and G from a qubit to a qubit, then this operation corresponds to applying them, each of them to one qubit. Qubit on the left flows in, qubit on the right flows in. They get transformed separately from each other, and then they come out in parallel. So this is really parallel composition as an operation. And here is where things get a bit more complicated. If you've seen more traditional sort of quantum information, quantum circuit formalism, this is what's written typically as a tensor product. So it goes from 2 qubits to 2 qubits. So this is 2 qubits and 2 qubits. And this is just a tensor product. Now, if you try to write them as matrices explicitly, the sequential composition is just the usual product of matrices, which is not, to be fair, too hard to do. But the parallel composition is what's known as the Kronecker product of the matrices, which becomes larger. And so you have a problem with the scaling of your notation, which typically doesn't go away very easily. Here, I'm going to say that it's this. And so what you get is, instead of multiplying two 2x2 matrices into a 2x2 matrix, you get the two 2x2 matrices become 4x4. Three 2x2 matrices become 8x8. So it grows, the representation, when you draw them next to each other, is just two boxes. But when you try to explicitly write them as a matrix, they grow exponentially. So by avoiding this sort of opening up of the boxes and just keeping them drawn in this diagrammatic formalism, we avoid this extra information that we'd have to represent. And for some large enough circuits, this becomes problematic. In fact, for most quantum circuits, it becomes problematic very quickly. So that's the idea of these sort of pictorial representations. This would be G, 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 just a 2x2 matrix. And the issue is that this grows, matrices grow exponentially. So they become impossible to handle very quickly. If you have multiple processes in parallel, it becomes very hard if you want to write them down in terms of quantum, in terms of sort of quantum states and unitary matrices. Okay, what do we do with this sort of parallel composition? Why do we need to talk about parallel composition? Well, because in quantum information, quantum computing, is the parallel composition a bilinear map, or it can be a multilinear map? So the parallel composition operation, or the parallel composition map. The parallel composition map can be anything. It's just a linear map itself, but the result of the parallel composition is a linear map. Let me draw it. 1 second. Maybe I can just do this. Fantastic. So if you have two linear maps, right? This is F and this is G. And you do the parallel composition, the result is this tensor product, which is itself a linear map. But it does have multiple inputs and outputs. So maybe this is the question that you were asking, or maybe you were asking whether you can do composition of maps with multiple inputs and outputs. In which case, the answer is yes. Anything you can put things together in any way you want, as long as you keep the inputs and outputs fixed, and then you can compose them in parallel. So as long as you mark the inputs and outputs and remember where they were, so say that this is Q0, Q1, Q2, Q0, Q1, Q2, Q3, and you remember that these are in the same order, then that's fine. So you can do it with a single wire on each end. You can do it with multiple wires on each end. However you want to put the two boxes next to each other, that works. But of course, these become very big very quick. So that's one of the nice things about this diagrammatic formalism, is that it allows you to do complex compositions without having to try and line up things. Does that answer your question?
Please, I wanted to know whether the composition can take more than two functions, because I'm seeing function of f and g. So can you have another function with h?
Yes, you can have as many.
All
So
right.
you can have this. This
yes,
one?
something of sort. Yes, please.
Yeah. So this, by the way, is something that I may have forgotten to say at the start. Please just unmute yourselves and interrupt me. I enjoy having questions asked. So it's you can ask them in chat and I respond, but you can also just talk if that works better for you. So if you have 3 of these, imagine that all of them are still 1 qubit to 1 qubit. The result of doing this is a matrix that kind of looks like this, where you have F at the outside. So you have 4 blocks that start with the coefficients of F. And then you have some blocks inside here, which start with the coefficients of G, each of them. So they're all the same, but they go G00, G01, G10, G11. Sorry, maybe not enough space. And here you get another block, which is H. So H00, H. Maybe I should really draw it larger. Give me a second. So used to. So F00. Let me take as much space as I possibly can. G00. And then you have H00, H01, H10, H11. And again, G01, and then you have H here, G10, and then you have H, G11, and you have H. So this is a very big matrix, you see? So this is again G times H, G times H, G times H. So this is 8 by 8 matrix. If you compose 2 of them, you get a 4 by 4 matrix. If you compose 3 of them, you get an 8 by 8 matrix. And more generally, if you compose in parallel n of them, so you have F1, then you have a bunch of them, Fn, like that. So this is Q1, Qn on n qubits. You get a 2 to the n by 2 to the n matrix, which is very, very hard to work with. It just grows exponentially large. Yeah. Then as to motivation, why do we care about this? Because some processes, some quantum processes don't take place in a sequence. Some quantum processes involve multiple parties. These multiple parties may be far away in space. The operations that they do are independent of each other. They're not on the same quantum state. They are on different quantum states. For example, we may imagine that there's 2 friends who jump on some rockets and they carry their qubits at opposite ends of the solar system. That's very fast rockets, faster than the ones we have today, but still. And that we can imagine that these qubits start in a very special state, which I'll discuss shortly, which is this state of 2 qubits. So this is Q1, QA, the qubit of Alice, QB, the qubit of Les. And these 2 qubits are entangled. So they're connected. Or entangled. And then they carry these 2 qubits far away in space, and they want to do some operations. And the operations that they do are in parallel. Now, if you want to describe a scenario where you have 2 qubits that have been carried out and then being acted on independently by 2 different parties, then Andreas' operation in Blaze's operation, so these operations are in parallel. So this is going to be some linear map on the left, some linear map on the right. So let's call this F. Let's call this G. And what you get is the same as saying I have a special component, something happens at the bottom, then 2 operations done in parallel on it. And this something that happens at the bottom happens to be a special state, which is called the Bell state. But that's not really necessarily part of the part of what we have to talk about. But if you've seen this, this is where time goes up. If you've seen quantum circuits, then maybe you have seen this particular quantum circuit. This particular quantum circuit starts by preparing 0, then applies typically a Hadamard, then applies a CNOT gate, and then you get 2 qubits. But in the quantum circuit formalism, boxes and wires are drawn left to right, so time goes up and space goes top to bottom. In these lectures, it's sort of rotated 90 degrees because we like to talk about physics and foundations rather than quantum circuits. It's still same principle. So you might have seen this. This is known as the preparation of a Bell state. This is the box that's drawn at the bottom here. It's this box here. Is this pi plus state. Cool. Now, when you try to connect multiple boxes together and you try to draw some very complicated processes, I think that's going to answer the question that's on the chat right now. So in a second, I will answer that. When you try to create complicated processes, you're going to wire many boxes together in different orders. Some of them will be before others. Sometimes there's going to be some box in between. For example, here we have a qubit, Q1, which goes from the box at the bottom to the box at the top left. But then a second qubit, Q2, like we can imagine that it sort of gets acted upon by this box and then goes here. You don't really know that it's the same qubit, to be fair, but you know that one of them goes in and then there's something which comes out. And so there can be some parts that go straight from the bottom to the top, some parts that go into intermediate boxes first, and then some parts that come out and maybe come out from boxes in the middle, some parts that get processed further and then come out. The point is there's no need to have, in this particular formulas, there's no need to have the same number of inputs and outputs. It really doesn't matter. As long as you connected wires in the right way, and you remember which ones are the inputs and which ones are the outputs. So you just mark them as like I0, I1, I2, I1, I2, O1, O2, O3, then that's fine. So you can really have any combination you want as long as your wires are connected right. And typically we pull all of the inputs at the bottom, all of the outputs at the top, so that we don't have bookkeeping issues. We don't like keep wires in the middle, but sometimes it is also nice to just remember that stuff goes vertically and you just don't draw really long wires that go all the way to the bottom. So there are some pictures that become complicated where it is more useful to just draw the wires in the middle and then just remember that some are inputs and some are outputs. So you could, I'll draw you a picture in a second to make that point again. But here, imagine that you wanted to give some actual meaning to these drawings. They're drawn with funny symbols just to remind you that there is no special meaning to these boxes unless you work with a specific theory, like quantum theory. But they could be anything. But let's say that we want to be a bit more symbolic, a bit more formal, and we give meaning to these. And so what we have is a state that gets prepared here. This is a state with 2 qubits. So we have a state with 2 qubits. We have some linear map that takes 2 qubits and returns 3 qubits. We have some linear map that takes 2 qubits and returns 1 qubit. And we have some linear map that takes 2 qubits and returns 1 qubit. So if we want to give this a bit more formal, more traditional semantics, we have a state, which is a state of 2 qubits. We have a map F that goes from 2 qubits. I guess I could start writing things properly. Let's say C4. This goes C4 to C8, because from 2 to 3. The G and H go from C4 to C2. or maybe I can be a bit more explicit and write 2 times 2 and 2 times 2 times 2 to remember that that's where the numbers come from. I guess, yeah. 2 times 2, 2 times 2 times 2, 2 times 2, 2 times 2. There we go. Now, this is kind of fine, except it is not the way that you would write the matrix in more traditional terms. So here, yes, okay, we've associated some linear maps to this, and that's all well and good. But in order to get a matrix out of this, I have to write down things which I can compose directly in parallel or in sequence. So first in parallel, then in sequence. So I have to make like layers, and then I have to write matrices for these layers, and then I have to sort of compose these matrices all together. This is just an example to show you why you don't want to use traditional notation to do this in general. And so what you start by doing is you start by taking the picture, and let's say, in case you want to ever have these slides, I'm going to keep some parts and remove others. So come on. Yeah. All right. That's one. Clean, clean, clean. Fantastic. Cool. So first thing you do is you write some layers, and you're gonna have to make some matrices out of this. And the first matrix is going to be your state. These are just the identity matrices for 1 qubit. So it's state times whatever this state is, by the way. It's gonna be, let's make it explicit. So psi 0, 0, psi 0, 1, psi 1, 0, psi 1, 1. So that's a state. Then you have to multiply it by the identity on one and on the other wire. So that's the first matrix. The second matrix is the identity times F. F is huge. It's a very big matrix because it's something that goes from 4 to 8. So it is a 4 by 8 matrix. It has 4 by 8 components. This is what F looks like. And then there's the identity on the right. This is the middle layer. And then there's the top layer, which has to be, let me clean this stuff as well. So I have space. And then the top layer has to be G, which is 2 by 4 matrix, tensored with the identity, tensored with H, which is also a 2 by 4 matrix. And then you have to compose these. So you take a product here, and you take a product here, and that's what your final matrix kind of looks like. So it's a very big expression that would require quite a lot of effort to just to write down, not even to.
Oh, hello.
Yeah.
Please, sorry, just to be clear, when you define the matrix, do those matrices represent the qubits, and then maybe the state?
So these represent some of them represent states, some of them represent transformations of states. Let me give you some examples. So here, an example of, let's say, a matrix that you could have as a linear map is let's say the Z rotations by some angle. And the Z rotation by some angle is a matrix, is a 2 by 2 matrix, which takes this form. So this is an example of a matrix that you would have. And this is a 2 by 2, right? So it has 2 rows and 2 columns. So it is a map from C2 to C2. This is what the matrix would be. But you can also define states, examples of states or their bras and cats. For example, you could have 0, which is this state here. You could have plus, which is this state here, where there's some normalization factor. You can have R, which is this state here, with a complex component at the bottom, an imaginary component at the bottom. So it's 1 over root 2, I over root 2. You can have many ones. The only reason I mentioned R is because when you then flip it upside down, you get the bra for it. And the bra for it is a row vector, which has the kind of the same components, but you have to take a complex conjugate. So it gets minus I over root 2. But these are just they're just complex numbers. As far as you're concerned, if you're not used to them, if this is not something that you do, this is what you just look at the boxes and have rules to manipulate the boxes and simplify the boxes and never look at the states inside. But if you come from a physics background and you want to sort of connect to what you've studied from a more physical perspective, then this is kind of the right way to do it. You just look at the boxes as linear maps. They're linear matrices. They're matrices, complex matrices. And the dimensionality of the matrices is determined by the number of input wires that gives you the columns, and the output wires gives you the rows. But remember that it's exponential in the number of rows, in the number of qubits in input. So if you have 1 qubit, it's 2 columns, 2 qubits is 4 columns, 3 qubits is 8 columns, 4 qubits is 16 columns, and so on. Same for the rows. If it outputs 1 qubit, it's 2 rows. If it outputs 2 qubits, it's 4 rows. If it outputs 3 qubits, it's 8 rows, and so on. In general, if you have a map that is any arbitrary number of inputs and outputs, so let's say that you have n qubits in and m qubits out, then this is a map that goes from C2 to the n to C2 to the m. So it has 2 to the n columns and 2 to the m rows. It's a very big matrix typically. These are 2 to the n and 2 to the m. This is what F would be, and this is a complex. It's a complex matrix. In general, that's what the boxes represent. And the states are special examples because row vectors are 1 by something matrices, column vectors are something by 1 matrices. So, sorry, one other way. Row vectors have 1 row. It's a matrix with 1 row. The column vector is a matrix with 1 column, but they're still matrices. So that simplifies your life. The special cases of sort of states and effects are given by the fact that if you have a state can have any number of outputs, so n qubits. And so this is something that goes from, you can think of it as a map that goes from 2 to the 0. So C, just C, but nobody really writes that. So you can really imagine that it is a row vector. It has 2 to the n rows, and it has 2 to the 0 equal 1 columns. And similarly for the tests, if you have n inputs, then this is a row vector which has 1 row, which is 2 to the 0, 1 row, and 2 to the n columns. That's the idea.
Sorry. But please, are you saying, okay, so the boxes are the same thing as the quantum keys, right? So,
yeah.
So what I'm trying to be clear on is, so that means that let's take C note, for instance. Does it mean it is represented as maybe as a matrix to perform its function?
Yeah. So let's take that example. Let's take an example with a C naught, right? So let's take an example where you start with 2 states in 2 qubits in the 0 state. Then you apply a Hadamard, 1 qubit, and then you apply a C naught to the 2 qubits. And you get 2 qubits out. Something like this. Yeah? So what does this look like? The 0 state is a recipe to produce a qubit. It's just a state. So it's a vector. It's a 2 by 1 vector. Okay, so it is a 2 by 1. Sorry, 1 by 2. No, yeah, 2 by 1. I wrote it correctly. The Hadamard is a gate. And again, remember that we are drawing time going upwards. The Hadamard is a gate. It has 1 qubit in, 1 qubit out. So it has to be a 2 by 2 matrix. It happens to be a matrix that can be written as this: 1, 1, 1, minus 1, with a factor of 1/2 in front to normalize it. So this is a unitary. It happens to be a unitary matrix in this case, but they don't have to be unitary. And this is a 2 by 2 matrix. A C0 takes 2 qubits in and gives 2 qubits out. And so you can represent it as a 4 by 4 matrix. And for the C0 specifically, the matrix is in this form. And it's 2 squared by 2 squared. So it's 4 by 4. Yeah. So you do represent them as linear maps, yes. And you just have some kind of composition that happens where you first compose things here and then compose things here, and then you get your state at the end. So if you try to do the composition, here you have to write down what this state is, which consists of preparing 2 qubits, both in 0, which turns out to be this vector. And then you can compose them together. And so the result is the output is a composition of 3 matrices. The C0 times the Hadamard times the identity, because this is just identity. So the Hadamard times the identity is this. Let me do it right. 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, and minus 1, 0, 0, minus 1. I think that's correct. Yeah, that's correct. Times the initial state, which is this. And if you compute it, what you get, like if you do this properly and you multiply these 3 matrices, what you get is what's known as the Bell state. So you get 1/2, 1, 0, 0, 1, which is the result of the composition. But you can also use, we'll see later on, well, I will not be able to show you, of course, but my colleagues will show you that if instead of doing it this way, you do it by applying some diagrammatic rules, then you can conclude a bunch of interesting things, and you can do the calculation more easily. And so what, I'm kind of a spoiler, I guess, of what my colleagues will do, is that you can start with, if you draw the states and the Hadamard and the C0 in the right way, like with notation that tells you what stuff is similar, what stuff behaves how. And that's what they will introduce. They'll introduce spiders, they'll introduce rules about spiders, they'll introduce fusion and color change and la-di-da. But the end result will be something of the following form. You're gonna start with something like this, where the notation is just a slight change from what we had before. And then you're going to first color change, then fuse, then fuse again on the other side, and then simplify, and you're gonna get something like this, which is a cap state. And this is going to be the Bell state. And you're not gonna have to do any matrix multiplication at all. You can just do it by applying some diagrammatic rules, which will be introduced later on. This is it's going to be a color change, and this is sort of fuse. This is fuse, and then you simplify. That pretty much takes care of things. Cool. All right. A few more things before we go. Just a couple of observations. One of them, I guess I don't need this slide. One of them is that when you draw diagrams, the only thing that matters is the way that you connect things together. It doesn't really matter where you move the boxes. The position of the boxes doesn't have any significance. This is sometimes known as only connectivity matters. So for example, you can take some wires, braid them together and unbraid them, and you can just pull them apart and that results in the same wire, which is kind of weird because if you try to do something like this in real life, you don't actually get the same result. I probably should have prepared this before, but hey. Some wires that I had, I happen to have wires. Yeah, pink wire, black wire, take the wires. Yeah, you braid them together. You start with the two wires, let's say at the top, then you braid them once, and then you braid them a second time, like this, which is kind of what the figure shows. Sorry. Like this, braid them, and then you braid them again. I can't seem to have, this is what I wanted, this. Yeah, the problem is that this sort of doesn't pull open because the wires are, see, tangled. But for our drawings, you don't really have to think of them as wires that can tangle. Think of them as wires that untangle. You can imagine them being in 4 dimensions if you want something like that. There's no tangling of wires. You can, if you braid them and you braid them again, they always sort of pull apart as if you did a braid that goes on the same side both ways, like this, where you can then like pull them apart like this, right? Like that. So imagine that's the way that these braids work. The only thing that matters is where you start and where you end, because you start at 0, then you go right and you end at 0, and here you also start at 0 and end at 0, and on the right you start at 1 and end at 1. Start at 1, you go right, and you come left and end at 1. Then those are the same diagrams. Same with the diagrams below. You can check that indeed this Q0, let's call it, yes, let's say 0 and 1, 0 and 1 as the outputs. If you start from 0, you hit spade and then go out in the position 0. On the right, if you start in 0, you sort of hit spade again, go right, and up in 0. If you start in 1, you first hit hearts, then you hit diamonds, then you hit clubs, then you come out. And if you look at the second picture, maybe I should have drawn it a different color. If you look at the second picture, it's the same sequence of operations. So you start from heart, then you go to diamonds, then you go to clubs, you come out at 1 again. So it's the same diagram. I've just moved the boxes around, but that doesn't change it significant. It would change if you try to make matrices, it would change the matrices that you get in between, but the product of the matrices in the end would give you the same result, is the idea. Sometimes this is something that doesn't come directly from the wirings alone, but you impose some equations by hypothesis. So you say, I am going to, or by, I guess hypothesis is not maybe the right word. You impose them by axiom. So you say, by axiom, you have some equation, you know to hold because, I don't know, you've looked at matrices and the matrix is the same. Or because there's some deeper significance to what the picture is. You'll see many of these. They're called rules sometimes. So an axiom or a rule. What you can do from a rule is you can derive other equations from that rule. So if you have 2 parts of a diagram that are the same, and the rest is connected by an equation, like as is the case here, right? You have the left-hand side here and the right-hand side here, but the heart at the bottom is the same fragment of diagrams, then you get an equality as a consequence. It's like equalities are closed under composition, if you want. So equations are closed under parallel and sequential composition. That's one way to, so equations give new equations by composition, which is good because you can start with some very simple rules, some very small rules, and you can then apply them in little bits of the diagrams and make two big diagrams equal by just modifying some part in between. That is one way to think about it. The more practical way to think about it is to say the process goes roughly as follows. I have a diagram, and inside this diagram, there is a part that I want to change using a rule. I want to sort of replace a little bit of the diagram with a part that is equal, but has different shape, different boxes, but I know it's equal for other reasons. I know the result is the same, even though the boxes are different and the wiring is different, but the result is the same. So one way to think about the process, diagrammatically, graphically, is that you have a part of the diagram that you want to replace. You cut it out, sort of cut it. You leave the hole there. You remember where it was. And then you paste the right-hand side of the equation in the same spot. Because equations have the same number of inputs and outputs, you'll be able to glue it back exactly as it was. You're going to just connect the wires as they were, but you get a different fragment of the diagram as a result. And the consequence is that you now get an equation between two larger diagrams. So you had an equation that said that if I take the first qubit of the diamond state and I plug it into the second input of the smiley face box, I have the same result as plugging the second qubit of the spade state and plugging it into the second input of the hearts box with this wire swap in the middle. Those I know by axiom or by rule that those are the same, or maybe I've already derived it separately. And now I use that equation to derive a bigger equation, which involves a larger diagram with the club and the squiggly snake at the top. So this is two bigger diagrams that are proven equal by using an equation between smaller diagrams and just cut and paste. So this is the way that we do equations in diagrammatic terms. Now, some equations are kind of trivial because the wires just connect the right way. So you get equations such as these ones, which I showed earlier on. Where is it? I guess I can show them. Did I not show them? Yes, I did. So you get equations such as the equations on the top there, like the braid is equal to the parallel wires, or this sort of cup, this snaky shape that I get by sort of making a wire go up, bending it down, bending it up again. I can just pull it taut. That's just connectivity. There's nothing interesting there. But I also get more complicated equations. So this is one of them. But I also get equations that say that I can, because the only thing that matters is where I connect the wires and the boxes don't really matter, I can just slide boxes around. I can rotate boxes. Rotating them typically changes, may be confusing if the symbols are kind of radially symmetric. Therefore, boxes are sometimes drawn with an asymmetric shape to be able to see whether they've been rotated or not. It's not necessary, but sometimes it helps, at least to sort of visualize what the process is. But the simplest thing you can do is literally take a box. If your box is connected on a band of wire, you can sort of slide it across the band of wire like a bead on a wire. And you get equations that way. You get an equation, the box on one side, the box on the other side. The diagrams are technically different, but it's just the same box connected to the same two wires, connected to the same outputs. So it's the same diagram overall. And you can similarly do it with a bend at the top. Like you take a box and you can slide it up to the right-hand side or to the left-hand side, and you get the same two different diagrams. I mean, they are drawn differently, but the connectivity is really the same. You've just rotated the box as a consequence. And there's no effect in this. And you can use this rule to simplify some fairly complicated diagrams sometimes. So imagine that you have a diagram where you have lots of processes that have been done in parallel and then in sequence and are connected by these cups and caps. And I'm not really, I think I can, I mean, this has some semantics. If I put in some effort, I could tell you what this means in terms of computation. And then you look at this process and think, okay, this looks complicated because I have a lot of parallel components, sequential components, and wires that connect them weirdly, but really they're just bends. So all I have to do is sort of pull all the wires taut in a single line, and the effect is that these operations that started being in parallel and in sequence are actually a single chain of operations that snakes through from the bottom to the top. And so I derive some more interesting equations this way. Why is this relevant? What can you do with this bending? It seems like a completely trivial operation, but next time, my colleagues will show that you can use it to derive a protocol known as the quantum teleportation protocol. So just by knowing that you can slide boxes around a diagram to derive equations between diagrams that look differently, you can show that you can show that a certain arrangement of operations that can be performed by, let's say, Andrea and Blaise at opposite sides of the solar system allow them to teleport a state from one end to the other. And so the spoiler, I guess, for this particular part of for the next lecture is the appetizer for next lecture, is that if you are at opposite ends of the solar system and you have a state like this diamond state that you want to move from one end to the other, and one way to do it is to just draw the diagram that does that. That takes a state and sort of transfers it from one side to the other. That is one way to do it. It requires some way of sending a qubit, which may be expensive. The other way to do it is to say, I can exploit this sort of sliding process by creating a situation where my diagram has a cup at the bottom, which is this Bell state, and then the two friends go at opposite sides of the solar system. Then Andrea on her side does something such that the resulting diagram has the diamond state that can be slid up, across, down, and then all the way to the right. And logically, this results to the state being teleported on Blaise's side. And what is it that Andrea has to do is just make it so that you could slide the state. That's just the only equation that you're using here is just sliding. You're just sliding boxes around, and it gives an interesting proof for a process, for a protocol that is otherwise very hard to describe. It is, if you try to write it down in terms of bracket notation or matrices, quantum teleportation is a complicated process. But if you draw it, it is not. It's just the mere observation that you can take a state. What is the operation that Andrea has to do? Andrea has to do something on her side that allows the state to slide around. What is that thing? That thing is like this band of wire, which turns out to be a cap, which is a process itself. It's a special process that will be discussed. And the result is, logically, this procedure, where there's a cup at the bottom, then the two quantum states get transported to opposite ends of the solar system, then a cap gets applied on this side, there's a diamond state, blah, blah, blah. The logical result is that the diamond state slides around, slides all the way to the other side, and Blaise has on his qubit the state that Andrea started from. So Andrea started with the state, now Blaise has it. That's the result of quantum teleportation. This sounds kind of magical, and indeed it is kind of magical to the point that it is forbidden by the laws of relativity. So the laws of relativity don't allow you to do this particular procedure, but there is a very minor modification that can be performed, which is going to be the entire point. So at some point I'm not sure if it's the next lecture or a few lectures from now, one of my colleagues will talk to you about the quantum lottery. We'll explain to you that some processes, sometimes you can coerce nature to do some things, sometimes you can't coerce nature to do things. Sometimes there are things that nature just, you can say, do this, and nature will pick one of multiple options, and you don't have any control over which one. And that's going to be the issue with teleportation, is that you want to do this cap, but you will end up doing maybe the cap or maybe something else which will disrupt your operation, and then you have to fix it and correct the error. That's for another day. I think I have done about an hour of talking for today. So I'll stop here. Thank you all for listening to me. I hope that you find it like thought-provoking at the very least, and that you look forward to the rest of this lecture series.
Thank you very much.
My pleasure. I don't know if there's questions or if there's time for questions. That I leave it to you to decide. I have some time in front of me. All right. Well, thank you, everybody. It was a pleasure. Till next time.
Thank you very much, Stefano and Katrina. We really appreciate today's lecture, and we look forward to hearing from your other colleagues to improve upon the knowledge that you have come to share with us. To our participants, we say to all of you, thank you for making it up for today's lecture. And as you have seen, he has just given us the tip of the Hashberg. It means that there's more to come in how to deal with using diagrams to solve quantum computing issues. And so we will look forward to that, and then we'll see to you. I think for the slides, he will make it available to Katrina, and then we'll place it in the e-learning platform. And so you can all check on it. And as I shared some document also with you, you can make time to go through the document so that you can also improve your knowledge about it. Once again, I say good evening or good afternoon to everyone, and hope to see you in the next lecture. Thank you very much.
Thank you.
Thank you very much. See you next time. Bye-bye.
Thank you.